different, we'll take a look to the different testing methodologies in the frame of fracture mechanics to evaluate this fracture toughness, and then a comparison of the different fracture toughness parameters to see the main similarities and differences between all of them. And finally, we'll see the relationship between the fracture toughness and tensile properties, which is also important to keep in mind. And finally, some remarks on other aspects important related to the fracture toughness characterization. Well, first, the first question is why is fracture toughness important, or why we should measure fracture toughness in these high-strength metal sheets? Well, as you know, with the emergence of these new high-performance sheet materials with increasingly higher strength for the construction of lightweight structural and safety-related components, for example, in the automotive industry, materials with really high strength, such as advanced high-strength steels, ultra-high-strength steels, or high-strength aluminum alloys. Well, these materials, the problems related to the cracking resistance, to their limited ductility, are more and more frequent. So these problems, like the problems of edge cracking during cold forming, in damaged areas, in punctured areas, in trimmed edges, and so on, or also the formation of cracks during impact loading, where the material is subjected to a severe plastic deformation. Then these fractures, or this kind of fractures, which are related to this crack initiation and propagation resistance, to the cracking resistance of the material, at the end to their damage tolerance, should be addressed to the material property that controls or that governs this initiation, propagation resistance, and the damage tolerance of the material, which is the fracture toughness. Then, well, we have seen all over these years in different research works that fracture toughness is indeed a good material property, a suitable material property to define all this fracture behavior of high-strength metal sheets. Now, also the key question is how to properly measure fracture toughness. Here, the first important message that we want to make is, well, fracture toughness cannot be estimated from tensile properties. It is often assumed that steels or material in general with greater elongation or with greater area under the stress strain curve, or for example, the greater UTS by total elongation product, which is usually also used as a toughness indicator. Then these parameters are related to the fracture toughness of the material, but this is not true. So we will see later also. But the important message is that we have to forget about this concept or this approach to trying to estimate fracture toughness properties from the tensile properties. Now, the correct framework to evaluate this fracture toughness, understood that this crack propagation resistance, or the resistance of the material to propagate the existing defect, should be measured in the frame of fracture mechanics. In particular, since we are talking about the materials with high ductility or ductile metals, in particular, we should consider elastic plastic fracture mechanics. Of course, this fracture mechanics field, or fracture mechanics approach is well established in different sectors where the structural safety is vital, like for example in nuclear and in oil and gas piping and aeronautics and so on. However, in other sectors, maybe mainly because of the complexity of these fracture mechanics testing procedures, these procedures are often not considered. However, as we have seen with the emergence of these new high-strength materials, high-performance materials, the need for knowing the fracture toughness properties of these materials is becoming more and more relevant. Well, there are different standard methods to evaluate this fracture toughness in the frame of elastic plastic fracture mechanics. Some of the most popular ones are the ASTM E1820 or the ASTM E2472, or the equivalent ISO standards 22889 or ISO 12135. And now, well, we'll take a look to this standard define different methods of different procedures to evaluate fracture toughness in terms of different parameters like the J integral, the crack tip opening displacement, or the crack tip opening angle, and so on. Now we'll take a look to some of these different methods and what are the advantages and limitations when when using these techniques to thin metal sheets. First, let's see the J integral. Let's talk about a little bit about this J integral procedure. Maybe it's the most known or the most well-established procedure to evaluate the fracture toughness of the ductile metals. The procedure you can measure the J integral following the procedure described in the ASTM E1820. This standard describes two procedures: one basic procedure to evaluate a single initiation toughness value, or J1C, or a resistant curve procedure to evaluate this J resistant curve, like in here, like you can see in the image, where the J values are plotted as a function of the crack extension. These J1C values, or the single initiation toughness value, it is known to be very conservative when the material has a significant contribution from a stable crack extension. So in this case, the full J resistant curve should be provided. Now, an important consideration to make here is that this standard procedure is intended to evaluate the plane strain fracture toughness of metallic sheets. So the thickness requirements described in this standard cannot be satisfied by thin sheets like the ones under consideration. We are talking from sheet thicknesses ranging from 1 to 3 millimeters in most of the cases, in the case of the automotive sector. But then this means that these thin sheets are in plane stress, which means that all this fracture energy has an important contribution to the out of plane deformation or local necking. Then all these fracture toughness or these fracture related parameters in thin sheets under plane stress condition depend on the thickness. So this is important to keep in mind when we're talking about the fracture toughness, all the fracture toughness parameters that we will see today, and when talking about plane stress fracture toughness in general, it's important to keep in mind these toughness values depend on the thickness. So it's not a material property itself, but it's a constant for a given sheet thickness. Well, this procedure is quite complex. The experimental procedure is quite complex, and the specimen preparation also, it requires exhaustive specimen preparation and the monitoring of the crack growth during the full test. The standard defines different methods, like the compliance method to evaluate this crack growth, but also it can be measured with alternative systems like video or traveling microscopes, etc. Well, as I said, also the data post-processing is quite complex, but of course it can be, you can do it. Then remember that one of the limitations, as I said, for these testing methods is the thickness requirement. So the specimen geometries described in this standard procedure, if you cannot apply really the recommendations given to thin sheets, because usually the specimen geometries are based on a proportion with respect to the thickness. We're talking about the 2 to 4 times the thickness, since we are talking about thickness of 1 or 1.5 millimeters. This makes the specimen, so the specimen size is not practical for testing. But if you use alternative specimen geometries, so not taking into consideration these recommendations used or provided in the standard, you can also evaluate these J-resistant curves. For example, you can construct a compact tension specimen, as you can see here, with the proportions, for example, following the proportion or the recommendation of alternative standards like the ASTM E561, which is less restrictive concerning this thickness dependence on the specimen geometry. Actually, it makes no mention to the proportion so the proportion of the specimen size is not based on the thickness. So you can use this kind of specimens. Also, alternatively, these double-edge notch tension specimens, which are these rectangular specimens with 2 symmetrical cracks. Then, using this kind of alternative specimen geometries, you can also use similar or equivalent procedure to evaluate these J-resistant curves in thin metal sheets. Here, well, as you can see here, this is an example of the J-resistant curve obtained for this kind of specimen. Here you will see that this curve is slightly different to the one described in the ASTM, because here we identified these 2 different parameters, being this Ji, like defined as a J integral at crack initiation, which can be understood as the point where let's say when the first small or the first crack advance is detected by a video camera located on the next to the surface of the specimen, and then this JC value obtained by this this 0.2 millimeters offset line as suggested by the ASTM. So following a similar procedure, we can obtain this fracture toughness parameters in thin metal sheets. We have used it, for example, for evaluate the yield resistant curves of different advanced high strength steels from thicknesses ranging from 1.4 to 1.5 millimeters. Here we have some results for a complex phase, a well phase, and two third-generation trip-assisted steels. Here, what is interesting to note is, well, this is the resistance curve for two specimen geometries, different the specimen shown in the previous slide. This the circles correspond to this double edge notch tension specimen, while the squares correspond to the compact tension specimens. One interesting thing to note here is that this yield resistance curve depends on the specimen geometry. Of course, because these J integral values along the resistance curve have an extrinsic contribution to the fracture energy from the plastic work dissipated. So in turns, this plastic work depends on the constraint level, so it depends on the specimen geometry. But interestingly, also this Ji or these initiation values, Jc, as determined at the, let's say, at the onset of crack propagation, are quite independent of the specimen geometry. So, well, in summary, we can see that using alternative specimen geometries, we can apply this J integral procedure as described in the standard and determine this JC. This is the J integral again, near the onset of a stable crack propagation, as determined by this offset line. It is important to keep in mind also that this is not a crack propagation resistant value, but is rather related to the initiation, or let's say, by definition, is the integral point near the onset of stable crack propagation. And also it's important to keep in mind also this yield resistant curves depend on specimen geometry, so this is not a property of the material. Now, let's take a look also at other interesting alternative method, which is the essential Walker fracture. The essential Walker fracture, as I said, is a very interesting method. It was developed by the end of the 70s as an alternative method to evaluate this plane stress fracture toughness of thin metal sheets. And the method is based on a simple idea. As I said, this fractured energy during a ductile fracture process can be split into two terms. One, the essential Walker fracture, which is developed in the fracture process zone, which is on let's say the fracture toughness itself, the energy to generate new surfaces at the crack tip, and also an extrinsic or an outer non-essential plastic work. Remember that I said also that in the J resistant curve, all the points belong, so have an extrinsic contribution from the plastic work. So this is the same idea. Okay. Then, well, this specific essential Walker fracture, which is again is developed in the fracture process zone, so it depends on in the cross section. It occurs, let's say, in the crack plane, while this outer plastic work depends on the volume. Okay, this plastic work surrounding the fracture process zone depends on the volume. Then if we normalize this equation like this, we have this final equation, this final form, which is reminiscent of a straight line equation. No? When we have the y coordinate or the ordinates, let's say the independent term, and also the gradient, no? multiplied by the variable. So how can we experimentally separate both terms? This is a simple method, and very interesting, clever way to separate both this essential Walker fracture and plastic work. If we test a series of specimens with a similar geometry but with different ligament lengths, with the ligament length is this uncracked area or the distance between two notches. In this case, this is a double edge notch tension specimen, which is the recommended specimen for thin metal sheets. But of course, in principle, any kind of a specimen or fracture mechanics specimen can be used. In the case of thin sheets, it's recommended to use these bent specimens because also the stress during the full test is tensile and there's no problem of buckling and so on. So this is the most recommended one. Then, well, in summary, we test these specimens with different ligament lengths, and we can, so plotting this load versus displacement curve and integrating the area under this load displacement curve, we obtain the total work of fracture. As we can see here, for increasing the ligament length, of course, this total work of fracture increases. The energy for fracture is larger. Then dividing this work of fracture by the cross section, something remember like the equation, we divide or we convert this to a specific work of fracture values, and we plot it as a function of the initial ligament length. We obtain a plot like this, and then we can separate this both the essential work of fracture and the plastic work by making this linear regression and then obtaining in the intercept, remember this independent term, which is in the intercept, this specific essential work of fracture, and the slope indicates the plastic work. Well, the most interesting part of this method is that it's a simple method if compared to, let's say, to the other fracture mechanics standard, but mainly because you don't have to monitor or to follow the crack advance during the whole test. So you can test specimens up to the final fracture and then measuring this energy, and you can easily evaluate this essential work of fracture. The main result, let's say, the fracture toughness value that we obtain here is this specific essential work of fracture, which again is obtained represents an average crack propagation resistance, since of course it's obtained from a series of energies for the complete fracture. So it contains contributions from crack initiation and propagation resistance. Then, although in the literature often it is said that this specific essential work of fracture is equivalent to the JC, the JC value obtained from the J integral procedure. We'll see later that it is not necessarily true. Also, I forgot to mention also when we're using also regarding the notation, as you have seen, we have used. I mentioned JC to avoid not J1C, which is often used to it's used to refer to the plane strain fracture toughness. So to avoid the confusion between these parameters, since we are in plane stress, as I said, we use the JC instead of J1C. Also, an interesting part of this essential work of fracture is that it allows separating the contribution from initiation and propagation resistance. As I said, this specific essential work of fracture is an average, so it contains initiation and propagation, but we can also measure essential work of fracture or fracture toughness at crack initiation by integrating the area only up to the point of the crack initiation. In this case, it could be detected, for example, with a BBO system or similar. When we calculate or we evaluate this fracture energy, contrary to the total work of fracture, this work of fracture initiation is quite independent of the ligament length. So by making an average of these values, we can obtain this toughness at initiation on this essential work of fracture at initiation. Also, an important thing to mention here is that there is not yet a standard method developed to measure the fracture the essential work of fracture in thin metallic sheet. There is a testing protocol developed by the European Structural Integrity Society, by the ESIS group, which actually was developed to measure the fracture toughness of polymer films, so of polymers. Then there are no recommendations regarding specimen preparation and so on for metallic materials. In this sense, we have been working also in a recently finished European project called From Planet in the development of this thin workshop agreement, which is like the first step towards the standardization of the method, where we have been working with different relevant companies of the sheet metal industry and other standardization institutions like UNE and DIN. And we have developed this method where we describe the methodology, also recommendations about the specimen geometries, the specimen preparation, and so on. So we hope that this is like a first step to standardize the method and also foster their implementation in the sheet metal industry. Here are some examples of application of the essential work of fracture methodology to different advanced higher strength steels, or similar to those shown before with the J integral. We have for CPs, DPs 1000, several DPs, so trip-assisted steel, third generation trip-assisted steels, and press-hardened steels, TWIPs, where we can see here, again, remember the specific work of fracture, which scales with the ligament length, and then by linear regression or by extrapolation to zero ligament length, we can obtain the essential work of fracture, while the slope of this linear regression indicates the plastic work. As we can see, this is a very useful tool to define the different fracture behavior of the different materials. So we have validated this. Of course, the method has been used a lot over the last years, mostly in polymer films and also in other ductile metal sheets, aluminum alloys, ductile steels. But we have been working a lot with application to advanced high strength steels to understand this different fracture behavior. Now, well, as I said, this is an interesting part of the essential work of fracture. Is also it allows to separate the contribution of initiation and propagation, being essential work of fracture related to propagation, but also we can obtain this toughness initiation. But we can see here, this is a summary of results for a wide range of advanced high strength steels, is that while some materials present a small contribution from crack propagation resistance after the initiation, that these materials that this fracture toughness at crack initiation, represented by these black circles, and the specific essential work of fracture or the squares, the empty squares, are pretty the same. So are almost equivalent. It can be considered almost equivalent. However, we can see also that there are other materials where there is a large contribution from crack propagation resistance after initiation. In this case, highlighted here in blue, we can see that there's a large difference between the specific essential work of fracture and the initiation toughness. Then in these materials, this essential work of fracture defines much better the overall fracture performance. And a single initiation toughness is not sufficient to define the fracture performance of this kind of materials. Finally, let's talk a little bit about other interesting method that has gained increasing interest over the last years. It had been also having used especially to characterize the tear testing of aluminum alloys. This is the can type tear test. Actually, this test was developed also to evaluate this notch resistance of aluminum alloys. And the procedure is described in the ASTM B871, although this standard was withdrawn in 2017. But of course, it could be still applied to evaluate this notch resistance of this toughness, let's say relative toughness of the material. Well, this test consists in pulling this can type specimen, which is a single edge notch tension specimen. The standard recommends the use of a really sharp notch. They recommend to use fatigue cracks, but of course, if you want to go for more accurate values, you can also nucleate the fatigue crack in the notch. Then you pull this test up to fracture, and you have this is the characteristic load versus displacement curve that you obtain with this kind of test. Then by integration of the area, you can also obtain these two parameters, this unit initiation energy, which represents the area up to the peak load, is related to the notch resistance to nucleate a crack, and then the unit propagation energy, which is the energy of the area under the curve after the peak load until the final fracture. And this represents the crack propagation resistance of the material. As I said, this is a very simple method because and it has been very interesting for a fast, let's say, screening of materials. So, however, it's important to take in consideration that it's not a material property. So, as the standard suggests, it must not be considered a fracture toughness value itself, but let's say a toughness index. Of course, the geometry and the test setup is quite simple, and it can be combined with also with digital image correlation, which is also very interesting to obtain different parameters. However, we will see that we must be careful when considering the results of the different testing methodologies. Again, some results of this kind of methodology of the CAN-type tier test for advanced high-strength steels. Again, we can see, well, the methodology is feasible. It can be applied to this kind of thin metal sheets. So we can separate this unit initiation energy and unit propagation energy and obtain also a material ranking according to this parameter. However, let's see what happens when we compare the different fracture parameters obtained from the different methodologies, which is interesting to understand a little bit more what are the meaning of the different fracture parameters and what are the most appropriate in this case, when we want to measure the crack initiation or the crack propagation or the overall fracture performance. And so on. Well, here we did this exercise to compare these different fracture toughness parameters. In the left here, you can see the parameters related to the initiation, this JI value, remember described at the beginning, this essential work of fracture, a crack initiation, and this unit initiation energy. In general terms, we could say that this initiation toughness is quite independent of the geometry and the testing methodology and so on. So this is good because, okay, well, it's easy to measure this initiation toughness. Then what happens when we look at let's say at the crack propagation resistance values, which at the end will define the full fracture behavior of this material. Well, first we can take a look at the unit propagation energy. The first noticeable thing here is that in general this unit propagation energy overestimates a lot the crack propagation resistance if we compare to the fracture toughness values JC and essential work of fracture. But also, if we take a closer look, we look at the ranking, of the material ranking that we can obtain using this kind of testing, we can also see that we must be careful. For example, we're looking at this TBF steel, which is a third generation triple-assisted steel, which has an important contribution from the plastic work to the fracture energy. You can see that it has a really large unit propagation energy, almost comparable to the complex phase, and more or less equivalent also to the quenching and partition steel. However, when we look at the toughness values measured by EAC and essential work of fracture, we can see that the fracture behavior is totally different because the TBF shows one of the lowest fracture toughness comparable to dual phase. Okay, so that's why when considering this kind of testing, it's important to keep in mind what are we measuring or which are the contribution of the fracture and the plastic work. Now, comparing this essential work of fracture and JC values, as I said, often in literature, it is said, it is assumed that this JC and essential work of fracture are equivalent. We can see, for example, in the case where the essential work of when there is no large contribution from crack propagation resistance, that is to say, when the essential work of fracture is similar or is close to the initiation toughness values, these JC values, you can see here, green bars and the dash bars, can be equivalent more or less to the specific essential work of fracture. Okay, TP, TBF, QMP here. Well, here is larger. But what happens in materials with a really large contribution from the propagation resistance, like the complex phase? Here we can see that this essential work of fracture, as we said at the beginning, this represents the energy for the full fracture. So in this case, while this JC is only to the not the initiation, but more or less the initiation for a small crack advance. In this case, you can see that this essential work of fracture better represents the full crack propagation resistance of the material. In summary, what we have seen when trying to correlate the fracture behavior of these high-strength metal sheets, talking about edge cracking or the crack formation in the crash, we have seen that at the end, this essential work of fracture is the most suitable parameter to describe all this kind of fracture related to the overall fracture performance or fracture resistance of the material. Okay, now some I wanted to illustrate, because I said also at the beginning that one important message is that the fracture toughness cannot be estimated from tensile properties. So here we wanted to illustrate the correlation between the y-axis between the essential over fracture and different tensile properties, yield strength, tensile strength, or the average of the yield strength and tensile strength is sigma y, strain hardening or elongation values. As we can see, there is no correlation between this crab propagation resistance and mechanical properties or conventional tensile properties. So also the idea of the common way of thinking that is higher elongation, higher uniform elongation, total elongation, or higher strain hardening, it means a higher fracture toughness. We can see that this is not true. Rather, on the contrary, we can see that materials, or material in this case are steels, but with higher elongation values often tend to show also lower cracking resistance. Well, this is especially critical, say, in an advanced high strength steels, because usually these complex multi-phase microstructures, the deformation mechanisms that contributes to improve global ductility measured by this elongation or by the tensile properties, often can have a detrimental effect on fracture toughness. So again, important to keep in mind that fracture toughness cannot be estimated from tensile properties. This is also an important message when designing new materials or new microstructures, because as you know, well, these new materials design is mostly focused on the optimization of these global properties or tensile properties. But also we have seen that it's important to take into account this fracture toughness of this crack propagation system. Finally, to finish the presentation, so all the aspects to keep in mind when measuring fracture toughness is the influence of the notch preparation method or the influence of the notch radius, for example. As well known in fracture mechanics, that this fracture toughness, JC, essential work fracture, I think, depends on the notch radius until a critical notch radius is reached, so below which this fracture toughness becomes independent of the fracture toughness. But if we want to measure accurate values, or accurate fracture toughness values, we need notches as sharp as possible, and see also what the minimum radius possible. Here, I would also the similarity rates again with some to illustrate this influence of the notch radius when comparing essential work of fracture results for specimens with fatigue pre-cracks, which are the black squares, and with machine notches, notches machined by electrical discharge machining with a notch radius on 150 microns. We can see the results for the different steels, and we can see that the first that we can see is that this sensitivity to the notch radius depends on the material. So there are materials with a low sensitivity to this notch radius. There are others where the fracture toughness is drastically reduced to the half of the value obtained from using notches to when you use cracks. And well, this is important, to keep in mind also that if you want to measure accurate values, we have to keep in mind this, that we need notches are as sharp as possible, the more close to the fatigue pre-crack as possible. So in this same research line, in this context, we developed this testing tool because we know these fatigue pre-cracking procedures are expensive and time-consuming and require special equipment. So it's at the industrial level, it's difficult to implement this fatigue pre-cracking operation. So we developed this rapid notching procedure to try to introduce or to prepare sheet metal specimens, to introduce really sharp notches, as you can see here, with a notch radius of about 2 microns by means of a simple sharing process. And we can obtain also in a few seconds these really sharp notched specimens that can be really used to evaluate the fracture toughness. Of course, this tool has been validated for different advanced high-strength steels. Again, here on the left have some results with the specimens both obtained with fatigue pre-crack specimens and with the specimens obtained with this shared notches for a wide range also of advanced high-strength steels. We're also still validating the results in different aluminum alloys and other stainless steels and so on. But what we found here is that this tool, it's a very interesting tool to obtain equivalent or let's say reliable fracture toughness value in a very short time. We are talking about a reduction. We need for fatigue per cracking around 90 minutes per specimen. It's an average time of 3 working days for testing the material, but with this new procedure we can test it only in a few minutes. And well, the aim of this tool was to try to implement, was to foster the implementation of these techniques also at a more industrial level, making easier or more accessible to the industry this fracture toughness testing procedure. And that was my last slide. Thank you very much for your kind attention, and well, I hope there are questions.
Well, thank you, David, and well, my apologies for the beginning of your talk. I was not well awakened, and just so that I was not introducing it correctly. So I forgot to say that you are from the Eurecat Research Center close to Barcelona, which is very dedicated to the development and the use of this technique. So sorry for that. Well, I see that in the planning there are some time that is planned at the end of the 3 talks for discussions. So except if you have one question that cannot wait for the next 2 talks, what I would like to suggest is that you write down your questions, and we will come back to a general discussion at the end after the 2 other talks. I think it will be more dynamic and preferable to keep to keep the planned schedule. Okay, so let's switch to the next talk, given my very close colleague, so Thomas Pardoun from University of Louvain, and so we will keep the topic of the method and go in maybe some more details on the physics and mechanics of what is behind this essential work of fracture. Please, Thomas.
Thank you, Pascal, and thank you, David, for excellent presentation and setting very nicely the stage for what I prepared for today. Share. All right, I hope you see the slides correctly. So the idea of this presentation was to go a little deeper in the true meaning of the essential work of fracture. And David just before made already some important comments about aspects in which I will dig into in more details. So I would like to cover a few basics, and I will not repeat what has been said before, so I will go quite quickly. Give some more physical and micromechanical understanding of what does it mean exactly, this essential work of fracture. And then I will come to one of my preferred topics, which is the effect of thickness on the value of the fracture resistance of thin sheet that you measure with the essential work of fracture or with another J1C or other approach. By understanding better this effect, it reveals the physics of fracture in thin sheets and gives additional insight on the meaning of the essential work of fracture. So I prepared a very fancy coverage of what is the essential work of fracture. I took notes that I prepared last year when we were so last year I gave a very short introduction to the students when we were during lockdown. And so I worked on paper and then I took picture from my phone. And so I have another presentation, but I don't know, I like it to show it that way. So very, very basic. You start with a test specimen. And I just want to introduce the concept of fracture process zone. So at the tip of the crack, when you load the specimen, of course you develop a diffuse plastic zone, but you also concentrate the plastic strain and the damage in a zone which will ultimately be the zone in which the material will fail. And this is called the fracture process zone, and the French name is zone d'élaboration de la rupture, so fracture process zone. And there is a well-defined definition for the fracture process zone given by Broberg. It is the volume of material in which at some point the failure process, the plasticity, the damage and failure process will localize. So it's a zone of finite dimension. Huh? And so the dimension of that zone will scale with a length which I will call x0. That will be the length, and more important is also the thickness of that zone, which I will call also x0. I will assume that this zone is more or less equiax, which is not completely true, but that fracture process zone is really where the failure process takes place, and this is the zone in which the failure fracture energy will be dictated. And T0 is what I will use as thickness of the specimen. The essential work of fracture basically is the work spent per unit area inside the fracture process zone. And during propagation, and that was already alluded by David. So that's important. And then comes the question, so what is exactly the fracture process zone? And there is something in terms of physical dimensions, and there is something specific with the essential, the thin sheets, is the fact that most of the time we get crack tip necking, and that will dictate the size of the fracture process zone. All right, so essential work of fracture, basically the question is how to separate the work spent in the plastic zone and the work spent in the fracture process zone. And the beauty of the approach of the essential work of fracture is based on dimensional reason to express the total work, W tot, as the sum of the removed plasticity and the work spent in the fracture process zone while the crack is propagating throughout the entire ligament. And just based on dimensional consideration, fortunately, what you find is that the plastic zone work is the contribution depends on ligament length and not anymore the essential part when you define the total work by the ligament cross-section area. And that's the way you can separate the two terms and get access to the essential work of fracture. And there are several rules, and David mentioned some aspects, but Antoine later will give more information about the region of validity and the statistical relevance, etc., of the measurement. So I will not talk about that. And you understood the idea. You make measurements with different ligament lengths. You measure the total energy, which is very nice because that means you don't need to monitor crack propagation, which is the difficulty in fracture mechanics and JR curve testing. So you don't need to know where is the crack. You just load the specimen till fracture. That allows also working easily on materials at high temperature, for instance. You don't need very sophisticated monitoring of the cracks, nor sophisticated extensometry. Anyway, so that was already covered before. I just rephrase it for some aspects in my own work. The meaning of the essential work of fracture. So first of all, it's extremely important that we should, an error that is often made when explaining the essential work of fracture is to consider it as a regression at zero ligament. Somehow this would be the work per unit area that you would get if you could take a very, very, very small ligament. That's not correct. It's not an extrapolation at zero ligament. The essential work of fracture is the constant term in a linear regression. So by dimensional, through dimensional consideration, you find that the total work is the sum of a constant term and a term that varies with ligament length. It does not say anything like, oh, it's the extrapolated values at zero ligament length. Of course, it is for mathematical reason, but don't try to put a physical meaning to that. And as a matter of fact, when you go to ligament lengths that are too short, the stress state moves from the near plane stress regime to plane strain. And what you see that you're losing the linearity. So this is very important. So don't talk about extrapolation or regression at zero ligament length. And again, more information will be given by Antoine about the limits on the size of the ligament and the selection of the ligament. The 2 points I would like to bring to your attention. First is essential work of fracture is not a cracking initiation quantity, like already explained by David, but I want to go one step further to reveal probably the main origin of this, the fact that the essential work of fracture should not be considered as a cracking initiation quantity. It is sometimes, but in general it is not. And a lot of things can be understood by understanding that the essential work of fracture is itself a contribution, a sum of two different contributions. One from an energy spent for damaging and failing of the material, and one contribution is in a work of necking at the crack tip. So let me go through that. And I will start with the last point, then I will jump to the previous point and then go back to this point. But I would like to start with the big picture. So let's look again at the dense specimen, double-edged knot tension specimen here, with a drawing here where you see the plastic zone, diffuse plastic zone, and the fracture process zone at the initiation of cracking. And now you see a zoom here of what is happening in this fracture process zone. And you see two things. First of all, in most metallic tin sheets that are sufficiently ductile, you see significant reduction of thickness at the crack. So it's really a necking process taking place at the crack tip, and which dissipates quite a lot of energy. And in the meantime, if you zoom in inside the material, you see also the development of damage and cavities that are nucleating, growing, and coalescing. And as a matter of fact, if you look from the perspective of the J integral, or you look from the perspective of the essential work of fracture, what you have is that in thin plates, well, let's start for a thick plate. In a thick plate, you basically have your total work, which I call here capital gamma, is the sum of the work spent in the fracture process zone, which I call gamma 0, plus gamma p, and the gamma 0 is essentially related to the work spent for growing voids at the crack tip. But in thin sheets, in thin plates, as you see below, now you have an additional contribution, which is this gamma n, the work spent per unit area to neck the material in front of the crack. And this is very important because that is the origin for which there will be a thickness effect. That is the origin of, most of the time, a larger fracture toughness in the plane stress regime compared to the plane strain regime. And it's also probably most of the reason for which there is a difference between cracking initiation toughness and crack propagation. So let me go to this question of crack propagation versus cracking initiation resistance for the essential work of fracture. So now I will go back to old works, and that was, so I had to go back to PowerPoint presentation I gave 20 years ago, and I can tell you that then the PowerPoints are not really reliable anymore. So, they're still open. I could still open PowerPoint presentation of the year 2000, but that was the limit I could see that the computer didn't like very much. Anyway, I went back to old presentations and I tried to modify it, and now I know that we can put nice colors, etc. So the schematic I'm showing here comes from a study we did at the end of the last millennium with colleague Yves Marchal and Francis Delaney. Francis was the head of the group in which we did our PhD, Pascal, and so he's the grandfather of the group, basically. And at that time, we were working on a 6082 aluminum alloy, and we did a lot of tests and a lot of essential work of fracture measurements, etc. What I would like to show first, and I will come back to this material later, but what you see in the schematic here is the ligament thickness and length. Blue is the original ligament. So you have the two crack front on the left and on the right, and the rectangle is the cross-section of the ligament. The orange line is what you see if you could stop a test just at cracking initiation and you could monitor the thickness, the profile of the ligament at that point. And so this is to show that there is a reduction of thickness, very severe reduction of thickness near the crack tip on the left and right side, and that is represented by the orange line. And the green is what you measure now really on the fracture surface at the very end of the test. If you take the specimen, you measure a reduction of thickness, which is TF. So the initial thickness was T0, and the final thickness you measure on the fracture surface is TF. And this reduction can be very high. If you want to see numbers for this aluminum alloy, and this is the same on many steels, you see that T0 minus TF divided by T0, which is the relative reduction of thickness, is in that aluminum alloy 0.6, so 60% reduction, which is quite high. But the point I want to make here is that at initiation, the reduction of thickness, I will call it T-tip. And T-tip is not equal to TF. And you see the green profile shows that there is a continuous reduction of the thickness over a length which is a transient length. And the exact values are given on the right graph as the open circle. And by the way, there are different thicknesses, starting thicknesses for that material. And what you see is that the T-tip, sorry, that's, I'll stop the phone. The thickness reduction at cracking initiation is smaller than during propagation, which means that during propagation, the necking expands more, which means more energy for necking. And so the work, the essential work of fracture being a combination of a fracture work and a necking work, the necking work keeps evolving and growing during propagation. And that's certainly most of the time the main reason for which the initiation essential work of fracture is not equal to the propagation value. And by the way, essential work of fracture is a balance over the propagation, which means that this transient length should be a small contribution compared to the total length. And so the essential work of fracture reflects more the work spent during propagation, is not much influenced by the initiation value. So there is a lot of confusion in the literature. I think now it's more or less accepted, but for a long time, people claim that the essential work of fracture was J1C and not J1C. Well, I think this is the explanation, and it complements what David has said just before. All right, let's move on. That was about the meaning of the essential work of fracture and also this question of necking and fracture. Now I want to go deeper into that point regarding the fact that the essential work of fracture, and as a matter of fact, J1C would be the same, is a combination of two contributions. And this is the core for understanding this not so well understood evolution of fracture toughness. And here I call it GC, but it could be essential work of fracture, or it could be JC, J1C. This is the evolution of fracture toughness with thickness. And if you read textbooks, like all textbooks and paper by Brook, etc., you see curves like the one on the left side. And you see that these different curves, you can find them. So sometimes what you see is when you go from high thicknesses where the plane strain regime dominates and you have the well-defined J1C, and you reduce the thickness, you see that the fracture toughness increases. Sometimes it seems to reach a plateau and nothing else. But often what you see is that the fracture toughness increases to a maximum and then drops down. Why is that? So understanding why the fracture toughness is increasing when decreasing thickness is easy to understand. You're slowly entering the plane stress regime. The stress triaxiality at the crack tip becomes lower and lower. So the local fracture strain at the crack tip can be bigger and bigger because the damage mechanisms are slowed down. But why do you get then a decrease and often a linear shape of evolution at a very small thickness? This has to do with the work of necking, and I will explain you that in a second. Other questions to understand this effect of thickness are related to the slant mode versus flat mode. So do you have a mode 1, mode 3, or do you have a flat fracture? And I will show you that flat is not probably the right word. Okay, and this is trying to understand better this evolution of GC. What was the purpose of a study we did in the lab together with Tony Atkins. So some of you recognize probably the name of Tony Atkins. He wrote a very good book on fracture of materials with very creative fracture methods. Okay, so let me go back now to this aluminium 6082. And we got exactly similar results for stainless steels, for different kind of steels. I will show you more results later. But this is probably the data set, the most complete data set we have is this data set on the aluminium alloy. So here you have the total work of fracture from which we can extract the essential work of fracture. So you see ligament length, work of fracture, and you see 6 curves for 6 different thicknesses. And what you find immediately is that the constant term in the regression, so the essential work of fracture, clearly increases with thickness, and this is seen now in the big graph in the center, where you see in the black dot, as a black dots, the essential work of fracture values as a function of thickness, and you see that the essential work of fracture increases linearly with thickness. So we really are in the left-hand side regime of evolution of fracture toughness with thickness. The J1C or JC, we should call it JC because we are not in the plane strain regime. You see it's smaller than the essential work of fracture and gets smaller and smaller, and JC reaches a plateau. So we are near the top of the curve, but we could not get points. We worked with a 6mm sheet at that time, and so we have no data for the unloading. Okay. Oh, let's go back to the point I made earlier. There is a contribution for necking and there is a contribution from failure. Can we go deeper into that? And from a better understanding, can we rationalize this effect of thickness? So now I'm going back to this now relatively old paper in which we try to separate these 2 contributions. So exactly as what we do for the essential work of fracture, where we try to separate the plasticity, extrinsic plasticity, and the work in the fracture process zone. Now we take the work in the fracture process zone, and we try to separate the necking work and a more essential, a super essential work, which we call gamma 0. And in order to do that, we develop a double regression effect, so, a double regression approach, where basically you do test at different ligament lengths and then you do test at different thicknesses in order to separate the gamma 0 from the work of necking. And as a matter of fact, what you find is that the work of necking, the total work of necking, is proportional to thickness. And why is that? The work of necking scale with the volume of the neck. And the volume of the neck is increasing with the thickness. And so it's proportional, it depends on thickness. And if you take the work of necking per unit area, what you find is that you will have a scaling with respect to the thickness. So by the way, look back at the result I've already shown before. You see that the essential work of fracture increases linearly with thickness, and that there is a constant term, and this term is the gamma 0, and the extra term here is the work of necking. Can we go deeper and try to put numbers on the work of necking and relate it to other quantities? So we tested at that time many materials, and as a matter of fact, these materials were coming from Tony Atkins, and he wanted to look at these materials from an archaeometallurgy viewpoint. So we worked with all these materials. I will not go into details, different thicknesses. And here you see the flow properties of the material, and the hardening law that we use is a so-called Swift hardening law with strain hardening exponent, and sigma 0 is yield stress and K is a hardening coefficient. All right. Why is it stuck? Okay. Let's look at the fracture surface of all these materials. We always find a cup and cup profile. So what you see here is a section, as you see on the right. So the thickness direction here, and the fracture surface has always this curved shape. And as a matter of fact, if you take the other specimen on the top, it has exactly the same shape. So it's not at all a slant fracture. It's really a bathtub shape, a cup and cup, if you want, which shows that basically the fracture strain in the middle is smaller than on the side. So the crack starts in the middle because the fracture strain is lower, and then you need more deformation to break the sides. But this is really a flat fracture in the sense that it's not a shear dominated fracture. Just the fact that the crack propagates first in the center and leaves ligament on the side, there is big crack tunneling, and it gives that kind of shape. We measured using this double separation of energy contribution. We estimated experimentally the gamma 0 for all these materials and the work of necking per unit volume or per unit area. So in this case, what you see is the ratio between the damage and fracture contribution divided by the necking contribution, both expressed in work per unit area. And then we have to take a specific thickness, because for each thickness you get a different work of necking. So we took 1 millimeter, typical sheet. And what you find for different materials is that sometimes the gamma 0 dominates. This is an example for this aluminum alloy. But for other materials, you see that the necking, the work of necking dominates. More you increase the thickness, more the work of necking will dominate, because the gamma 0 will remain the same, but the work of necking will increase proportional to thickness. And so, but you see, you can have the different scenarios, and the values are given on the right. Okay, perhaps I will go fast here just to show you, and if you are interested, please go in the paper. Don't hesitate to contact me if you have questions. But we developed a model for the work of necking, and we developed a model for the work of damage. I will not go into any details, just telling you that the work of necking, you can calculate it by integrating the plastic work that is dissipated in the neck as the neck progresses. So you have to integrate the work from the minimum from the center to the upper part of the neck. You have to integrate the plastic work to calculate, to get an estimate of the work of necking, total work or work of necking per unit volume. In order to do that, you assume plane strain condition in the direction of the ligament, which is known to be a very good assumption if you run 3D finite element simulations. There is one parameter you need to know. You need to know the expansion of the neck in the length direction, or in the elevation direction. So the neck is not necessarily a one-to-one shape, but it may be longer. And indeed, if you run finite element simulation and you look at the profile of the length of the neck, you find that the height of the neck and the thickness of the neck, they are not giving you a value of 1, which you would get for a perfect plasticity material, but you're getting a value that is larger than 1, and which will be larger and larger as you increase the strain hardening exponent. Larger is your strain hardening exponent, wider is your neck. It redistributes plastic strain, or it tends to delocalize the necking. But that's important, because that means higher is your strain hardening exponent, larger is the neck. And so more dissipation you can have in your necking zone. And we quantify this alpha parameter running a lot of finite element simulations. And we got even a empirical equation for that. Okay, so we estimated the value of the work of necking from this model, and I'm not going into details, and we compared the prediction with the experimental value. And of course, there is one parameter you're not predicting, but you're measuring, is the fracture strain. So one of the parameters that enters the calculation of the work of necking is the fracture strain. So meaning the strain at which you stop dissipating by necking, because basically it's broken. But you see the values here. It's not right on top. Of course, it's not right on top. And even for some materials, not very good. But it's semi-qualitatively, it's okay. So it shows that we can understand what are the key ingredients of this work of necking. So in the paper, you will find curves giving you, for instance, the work of necking per unit volume in a thin sheet for a crack that propagates, normalized by heel stress, normalized by this hardening parameter and strain hardening data. So these are basically your three hardening parameters. And you see here the value as a function of the fracture strain minus the strain at necking. Before necking, there is no work of necking. It's zero. So it starts at the strain corresponding to the onset of necking, and you get evolution which depends on the strain hardening exponent. Okay, that was for the work of necking. And once again, the work of necking per unit area evolves proportional with thickness. For the gamma zero term, it's even more, I'm not sure it was complicated, but this part is more complicated because we need a damage model to calculate the work spent to nucleate, grow, and coalescence void in a zone which is undergoing a stress state that is representative of the stress state at the tip of a crack in a thin sheet. Every word, what I said is important. So what I did at that time, I was working on damage. That this is my old subject. This is the subject of my heart. And I was using this complicated Gerson model with another coalescence model, etc., whatever the details, to estimate the work per unit area needed to break a material element that would be located in the middle of the neck at the tip of the crack in the dense panel. So I was applying a stress triaxiality that was corresponding to exactly the loading condition of a material point there, to estimate the evolution of stress with displacement and calculate the gamma zero. And you see the equation, the symbolic equation on the top, the gamma zero, this energy per unit area to grow voids until failure, normalized by the distance between voids and normalized by heel stress, is a function of different parameters. F0 is the initial porosity, and W0 is the initial shape of the void. And so we calculated this parameter for different strain hardening exponent, blah, blah, blah. We also compare the gamma zero to a J1C value that would be obtained in pure plane strain. And typically the value, you see the ratio, if you trust the model, and there are many, many assumptions, so it's just, we have to be careful, but the ratio of the two would be a factor 3. So the gamma zero, if everything is correct here, would be 3 times the J1C. And on top of gamma zero, you also have work of necking. Okay, in order to calibrate the model, I had to see if we could get good prediction of the fracture strain. So to fine tune the F0, I will skip these details. We also measure on the fracture surface what should be the void spacing by measuring distances between voids. So I will skip that. But the message, the final message in the paper was the following. We tried to predict the ratio of gamma zero over gamma n, and there are some normalizing factors there which make the result quite general. And so basically what you see on the curve here, I will not describe the details, but the ratio between gamma zero and gamma n with these normalization parameters, this ratio, it can get basically any value depending on the porosity in the material, the strain hardening exponent, etc. So basically you can have everything. And so that explains why people find sometimes that the fracture toughness first is increasing a lot with thickness, reaches a maximum, then decrease, and to an even lower value. But sometimes you may be in regimes where the work of necking is insignificant, and then you can have your fracture toughness decreasing down to plane strain. And this is still open for discussion for sure. And so I hope that by giving you this extra information, that helps understanding better what is behind the essential work of fracture. A final, just to show you that we have not stopped working on that. And for instance, Karim Ismail did a PhD together with Pascal and with me on advanced dual phase steels with comparing equiax microstructure and fibrous microstructure. And Karim did this painful set of tests to measure essential work of fracture at different thicknesses to separate the gamma zero and the work of necking. And the goal was to understand why this fibrous dual phase steel was much better than the equiax dual phase steel. And we wanted to know if it was coming from the necking or from the gamma zero, because that indicates where you have to go to improve even more your microstructure. Based on that, these are the conclusions, and I will not repeat them. Work of necking, work of fracture, essential work of fracture is a propagation quantity. Thank you for your attention.
Thank you, Thomas, for this well, clear and detailed analysis of the work of fracture. As always, I would say, once you start to go into the details, it can become quite complex, but you still show that there are some challenges and still things to understand. So
we're not getting younger, Pascal, with this.
No. No. Okay, thank you. So well, keep your questions or comments, and let's switch directly to the third talk. Still with an extra view or extra details or extra questions about this essential work of fracture method. So the talk will be given by Antoine Hilhorst, with in the final rush finishing the writing of his thesis also, but he took some time to summarize and present stuff he developed during his PhD. So Antoine, the floor is yours.
Okay, so you should be able to hear me, and let me share slides.
Yeah, we see your slides and we hear you.
Okay, so this is the beginning. I start from the top. Okay. So thank you for introducing me, Pascal, and I will build upon what David and Thomas said, because I will talk about some, so it says statistical aspects of the essential work of fracture method. And so during the 4 years of my thesis, I worked a lot with this method, and I had to make some improvements. So I'll talk about this. And so I constructed this in 4 parts, so I will give a brief context and motivation of this, and show then 2 ways I improved the essential work of fracture method. And then finally, I will give some guidelines I use to analyze my experimental essential work of fracture data that could be interesting for you. So let's start with the context and motivation. So I work with a lot of materials, star ductile, and I'm interested to measure the fracture resistance of these alloys. And as you saw, the essential work of fracture method is one of the best, if not the best method at the moment to characterize this. And so this method has several advantages. So you only need the load and displacement curves of your tensile tests. And so behind this also means that you do not need to record the crack propagation, etc. So it's a very nice advantage. And the second one, it's an easy, I would say, specimen preparation, because you do not need fatigue pre-cracking. But like David said, it's not as easy as that. It's just that you need the notch radius that needs to be small enough, but this is material dependent, and luckily for me, for all my material, I did not need to do some fatigue pre-cracking. But so the principle of the method that has been went over by David and Thomas already, so I will go fast about this, is to, inside the valid range of ligament length, is to find this linear behavior and to extract the constant term, which is the specific essential work of fracture, that is directly linked to your damage and fracture behavior. But so to do this, you need to measure for several ligament lengths the total work. And so that means you need a large number of tensile specimens. So this is typically fine in the industrial settings where you have a large quantity of material, but it can become a bit problematic when you have when you are working with expensive material or hard to process, or if your specimen size is limited from the initial sheet dimension. So in my case, I worked with material that we would process in the lab, and so I was limited both in size and also in the total quantity of material I had to work with. And so it was well, mandatory for me to find a way to reduce the total amount of material needed to perform the overall analysis. So I will show you how I improve the method with the goal to reduce the total amount of material while keeping the same statistical error on this extracted essential work of fracture method. And so I did it in two ways. The simplest way is just to adapt the specimen geometry to the ligament length, and the second one is to choose an optimum set of ligament lengths. So let's go over the first one. So Thomas briefly talked about this, but for the measurement to be valid, you need two requirements. The first one is that the ligament should be entirely plastic before the crack initiation, and the plastic zone must be confined to this ligament. And so basically that means we are in this case here, because if your ligaments, well, your notches is too far apart, the plastic diffuse zone will not interact between each other, and so you don't have this relationship where all your samples will be geometrically similar, and so you cannot have your total work divided in the two contribution. And in the other way, if the gap, the ligament length is too small, you start to have your fracture process zone that interact between each other, and the stress test will not be similar between each sample again, and so the method is not valid either. And so what you find in the literature is some bounds on your ligament length. So typically you see the lower bound to be between 3 to 5 times the thickness, and the upper bound is either linked to the width of your dent, so typically it's the third of the width of the half of the width, or this size of the plastic zone, so this is computed with the Irwin formula, but you also need to know some material parameter. But one thing to note is that these two are empirical values and they are not very well defined, so the bounds are not are a bit fuzzy depending on which material you use. But we can still take advantage of this. And so this is what I present on this slide. So typically what is done is to always have the same dent size for all the ligament lengths. So this is what I did with the series of tests in blue, where all the dents had a width of 50 millimeters and a height of 100 millimeters. And the second set is a series test with adapted sizes, where the width is twice the ligament length and the height is twice the width. And I did also a few more tests where I would keep the height the same, so it was a height of 100 millimeters, but I would vary the width between 20 to 50 millimeters. And I also kept the ligament length about constant, but since I need to prepare the samples, there was a bit of variance between the ligament lengths. Okay, so you see that the data is represented by the markers, and then I did the linear regression for both, so this is represented by the dashed lines. And so we can observe that the extracted essential work of fracture for both of the series are quite close to each other. However, what we also see is that I drew in dashed dot lines the confidence interval, so it represents like the spread of the value. And so if you look at ligament length 0, it would be the error on the EWF. And so we can see that for the red series, the spread of the value is a bit larger than for the blue one. So this comes from two contributions. The first one is simply a statistic, because for the blue set of experiments, we use 20 samples, and for the red one, there's only 14 samples. But also something I will show later, it's a bit hard to handle smaller samples, so we had a bit of difficulty to perform the mechanical test. And so the last thing I wanted to show in this slide is what you see at the bottom of the graph, which is a representation of the total amount of material that is needed for each of these points. And so just at a glance, you can see that the red one uses a lot less material than the blue series. And so here, this is what I was talking about smaller samples can be harder to handle. So we had a problem. So this was my first series of tests. So we were not as prepared as we are now to make this test, but you see that with the clamping rod that we used and with this material, it was quite the sample was rotating and slipping inside the jaws, and so you had a shift inside the material, which means that this is not valid. So you see on the force displacement curve, so the blue one again is for the identical sizes and the red one for the adapted sizes. But you see that it fits quite well for the beginning of the curve until the maximum. And then when the cracks start to propagate, sometimes you see that it slipped and the curves are not identical anymore. And so this is what explains a part of why there's more spread of the values. But still, later this has been solved by changing the setup. So we use now hydraulic clamping jaws, which is a lot better. But still, the takeaway message of this first part is that yes, it's possible to reduce the total amount of material needed just by adapting the specimen geometry. So the second point is now, can we choose an optimum set of ligament lengths? So typically what you see, and what David showed, for instance, is that between the two bounds of the ligament length, we choose a number of samples to test, and then we space them equidistant manner between the two bounds. So for instance, if we have 15 tests, we would try 3 tests at 5 millimeters, then 3 at 10, 3 at 15, 3 at 20, and 3 at 25. And we are happy with this. But a question that we can ask ourselves is that, is there a better way to place those samples? So for instance, maybe it's better to have more samples closer to the lower bound and a bit less samples at the upper bound, or maybe it's something different where you have half at the lower bound and half at the upper bound, but 1 or 2 samples in the middle. And moreover, now that we have our samples that are dependent, well, the sample size that is dependent of the ligament length, if we have more samples with a small ligament length, this means that we would reduce even more the total amount of material needed. But so, of course, we want to keep the error on the expected essential work of fracture the same or better than the equidistant case. So we need to define how we do things to be able to have a solution. So for this, we need to go back a bit to how we do the linear regression. So we assume that, so we have a set of data points. We assume that it is linearly distributed. And so we have our two parameters here for the distribution and some white noise that explains the variance of in the data sets. And so the OLS estimation, so ordinary least square estimation, is the most basic way to do linear regression. Is basically to minimize the square of the distance between the straight line and your data points. And this translates to this formula. So this is a very classic way to do linear regression. And in the case of the essential work of fracture, it's exactly this. So we have your total work, that is the sum of two contributions, one constant term, that is the essential work of fracture, and a term that is dependent on the ligament length, times a parameter, so the non-essential work of fracture, and a shape factor beta. But the important thing is that the ligament length is bounded by two values. So here I call them lambda min and lambda max. So here is how I set the optimization problem. So I have an objective function that is I want to minimize the total amount of material. And so a dense sample is basically the width times the height. Since my width and my height depends on the ligament length, the objective function for the minimization of the total amount of material is simply lambda squared times a proportion, because for each ligament length I can have more or less specimens. So my conditions are that simply the sum of this proportion should be equal to 1. And I impose two things. So I want that the error, so it is represented by the variance on the estimator, should be lower than the equidistant case. And this for both the intercept and the slope. So I will spare you all the mathematical developments and go straight to what I found out. And so this is summarized by this graph on the right. So there's two things I realized doing this. So first, it only depends on the ratio between the lower bound and the upper bound, so that I have here. And I only have two proportions, so this actually simplifies to just two fraction, which is the fraction of samples with the ligament length equal to the lower bound, and the fraction of samples with the ligament length equal to the upper bound. And so from the same model, I changed it a bit to consider three different scenarios. So the first one is the one I explained. So I just want to minimize the material, and it must be better than the equidistant scenarios. And so we see that to achieve this, we would need approximately 90% of all my samples with the ligament length equal to this lower bound, and the rest with the upper bound. Now, if I don't really care about the slope, I still want to minimize the material, and I still want to keep the error on the intercept, so the error on the essential work of fracture, smaller than this equidistant case. In this case, we have this orange curve, and we see that we even have a larger proportion of samples that has this lower ligament length, which sounds logical. And finally, I remove this objective function, and instead I use this one as an objective. So I want to minimize the error made on the essential work of fracture. In this case, what we realize it's the same. We still want to have more and more samples that has as ligand length the lower bound of ligand length. And so typically what I have, for instance, is the smaller ligament length possible is 5 millimeter for me, and the higher is 25, and so we would be at around 0.2. And so I would have around 85% of my total number of samples to have this lower bound of ligand length. What does it translate to in the fraction of material that is safe? So I compare the orange and the green scenarios to the equidistant case. So the fully constrained, we see. So I will take again the case that is close to what I work with, which is around 0.2. So when you compare the fully constrained solution against the equidistant case, we see that we save about 70% material. And for just the minimization of the essential work of fracture, we save about 50% of the material. So, but this is a bit statistical and mathematical model. How do I validate this model? So first, I try to validate it numerically, so doing a type of Monte Carlo simulation where I set the true behavior, which would be linear. So I would know these two parameters, beta 0 and beta 1. Then from this, I would generate a random dataset with different strategies, so either with more samples with lower ligament and less samples with larger ligament lengths, and then make a linear regression from this randomly generated set. So this would be in blue, and then I would compare the estimator to the true value. And so I summarize this in this graph. So again, I have 4 different scenarios. So I will go through first what is displayed on these figures. So basically, so it's the estimators minus the true value normalized by the true value. So the larger the spread around each axis, the larger the error or potential error you make using this type of scenarios. And so on the x-axis is for the intercept, so it would correspond to the essential work of fracture. And for the y is the slope of the regression. So we see in yellow, I have the equidistant case where the spread on the slope is quite tight, so this is quite nice, but on the intercept is quite large. And so we see, look, in red and in blue is the two distribution I developed with the statistical model. And so we see that the spread is a bit similar for the slope, but is a lot tighter for the intercept. So this is what we wanted. In the case of the values I took for this simulation, there's not a lot of difference between the two models here. But one thing you will realize is it doesn't feel great experimentally to just pick two other two bounds, because you don't really know what happens between them. And so you need a way to still validate that you are still inside this linear regime. So what I did in my experiments is that I still had more samples with lower ligament lengths, but I've been a bit more conservative, where I have a bit of a spread close to the lower bound and as well close to the upper bound. And so in this way, you still reduce a lot compared to the equidistant case, the spread of the potential error that you make on the essential work of fracture, but still better than, yeah. So the takeaway for this part is that, yes, again, it's possible to reduce the total material needed for by carefully choosing the ligament length. But the second thing that is shown is that even if you don't adapt the specimen size to the ligament length, you can still improve your error on the essential work of fracture by choosing carefully the ligament length. Okay, last thing I would like to show you is how I analyze my experimental data. So I will show you a typical example here. So this is for stainless steel 304L. So here you have the dense dimension and the number of repetition. And so you see, like I was saying, I stacked more sample with lower or smaller ligament lengths and only a few with larger ligament lengths. And so one of the big thing is, of the big thing to analyze your data is to identify where are the outliers. So the first thing you can do is something I already showed you, is to draw the confidence intervals, and so points that fall outside them can be identified as outliers. The second one is to draw the residuals. So the residuals would be the distance between your linear regression and your dataset, but normalized in a statistical way. And so again, a point that would fall outside your bounds would be identified as outliers. And finally, last thing that is interesting to do, especially for the essential work of fracture, is that you can do a linearity test. So the way it works is that you first define a linear regression from a few points. Then from these 4 points, let's say, you take the next one and you also make a linear regression. And then you compare these two and you have a statistical test to check if they are significantly different or not. If you cannot differentiate the two linear regression, that means that this point that you added must be part of the same group. And so iteratively, you add point by point and check each time if the point you add belongs to the same linear regression or not. And so I did this exercise for this set of values. And you see that there are 2 points that are rejected at the end, and this is the 2 red points that are already rejected by the confidence interval. Okay, so this was just for the basic linear regression methods. Next thing I would like to show you is how I use digital image correlation for my test as well to get some extra information. So DIC, so digital image correction, it's a very powerful tool to measure the deformation during the tests. So what you need to do is to have your tensile specimen that are painted with a speckle pattern, so as you can see on the right. And you record the tests. So in my case, it's 2 frames per second with 2 cameras and at high resolution. So to give you an idea of the resolution, the red square here is a 1 by 1 centimeter. And then after the test, you process all the images and you compare each pixel between each image. And so that way you can obtain the deformation during through time. And so this allows me to draw this type of graph. So it's quite a lot of information on one graph. So I will try to take a bit of time to explain them. So what is drawn on the left is the isocontour on your dense specimen. So in this case, it's a 7% strain isocontour of the total deformation at a point of time. So here you can see, well, you can guess where the notches were on my dense specimen. And so each color corresponds to a point in time on my force. Well, here it's force time, but it could be a force displacement. And so, for instance, if you take the light blue isocontour here, we can see that the deformation was localized here close to the notches. And why I do this is to check if the criteria for the validity of the method was met for each of my tests. And so one of the criteria is that the ligand must be fully plastic before crack initiation. And so since crack initiates about at the maximum force a bit later, here I can check that the whole ligament was plastic right before the crack initiation. So this is the first thing you can do. Second thing I like to do is draw these types of isocontours. So this is slightly different than before. So instead of checking from the beginning, I checked after crack propagation. And instead of drawing the total deformation, I draw the increment of strain. So for each color, it's at the beginning of the segment and at the end of the segment that I make the difference in strain. And so again, I make a contour so it's easily readable in the figure. And so what does it allows me to see is that I can check the shape of the plastic zone, and this way I can check that the plastic zone is similar or geometrically similar between different ligament lengths, which is also a criteria for the validity of the essential Walker fracture method. So in this case, I have a test with a ligament length of 10 millimeters, one with 15 millimeters, and one with 25. And the second point, we can check that the plastic zone is confined to the ligaments during propagation as well. Okay, so this is everything I wanted to show you. So thank you for your attention.
Okay, thank you, Antoine. Okay, well, thanks again to the three contributors, the three speakers. So we now have some time for discussion, for questions. So if you have questions, please raise your virtual hand, and we'll organize these questions as smoothly as possible. Yes. Sorry if I don't spell correctly your name. So Aiso. Yeah, you will have. Well, Pierre, you have to allow. Okay, you have the word.
So I'm here.
Yeah.
Aiso Atsuma, yes, indeed, from ToughSteel. For Thomas, you showed the strong dependence on the N value for the for the hardening exponent for the necking, the work done in the necking zone. So we make steel here in Amuiden, and we tend to think that the steel is very strongly strain rate sensitive. And if you have a strong rate sensitivity, your neck is also larger than you would expect. So did you also look at that? And that's a big difference, for instance, with aluminium. And maybe that explains the last noise that you still have, or what do you think about that?
It's an excellent point, very good point. Strain rate sensitivity is acting the same way as strain hardening exponent. And we know that by work also on titanium alloys that it could be an effect. So the rate sensitivity delocalizes the necking process and can contribute to a larger work of necking for sure. But we have not investigated that from a theoretical viewpoint. But it's a very good point, very interesting. And it's a way to go. I mean, there are applications where we're not using sufficiently this capacity to even distill some rate sensitivity. For instance, some nanostructured metallic alloys, they are claimed to be relatively brittle, but some of them, they regain ductility because of a higher rate sensitivity exponent at nanograin size. And that's why some of them, they are more ductile than what we think. Now, regarding fracture toughness, there are only very limited studies about that. But I fully agree with you. It's a very good point, but we have no deeper investigation on that.
Maybe next project.
Oh, yes.
Thank you.
Okay, thank you. Yeah, just to be clear, so you well, by default you don't have the capability of turning on your microphone, but if you raise your hand, we will give you the word. Huh? So yes, Tony Chezen.
Let's see. Yes. I have also a question related to the microstructure, because yeah, like the explanation and for Thomas, it's, let's say, from a continuum point of view, and there are this it was this part regarding the voids, but then if one would take into account also the microstructure and the fact that there is a certain crystallographic texture, different grain size, different orientations, so yeah, probably for that we would need a separate set of presentations. Could you comment on that?
No, for sure. What I've explained was a minimum model where we assume that everything is dictated by the damage process, without assuming anything regarding the grain orientation, etc. So it's known that the damage growth may be influenced by the crystallographic texture. We can also have a tendency for second phase particles to sit along grain boundaries and lead to a preferential path for the voids, and so that can trigger some clustering effect, etc. So all these distribution effects, they may play a big role, and this is something we're addressing in other researches, but not directly related to the question I addressed today. So of course there is a bunch of research and study on improving damage models, advanced Gerson model to take into account distribution effects and plastic anisotropy, etc. So, and also several populations of voids due to carbides on top of the sulfide manganese, etc. So, of course, so the message for today was more to help thinking about these two contributions and separate them from a more didactic viewpoint. But there are a lot more to do on understanding and modeling better the two terms. That's for sure. You're right.
Thank you. And maybe just a specific question for Antoine. So the work that you showed is based on notched specimens. So they are not fatigue pre-cracked or pre-cracked, or it's just an EDM notch, or?
It's EDM notch, and then it's pre-crack by a razor blade. By
razor blade.
Yeah, you make you thin the crack by using a razor blade and making a sharper crack to be sure that your initial defect is smaller than the critical opening, as David showed in the beginning.
So to give you an idea, for EDM, the size of the notch is around 200 microns. I would say 200 to 300 maybe. And with the razor crack, it's around 50 to 100 microns. So you can reduce a bit from the EDM.
Okay. Yes, thank you.
Okay. Well, just to advertise, and don't hesitate to go and see the website, toughsteel.eu. You will have some extra information about the project, the partners, details about some documents, extra next events, and so on. So well, feel free to go there and contact other partners of the project if needed. Now, if you have still questions, please. We still have a little bit of time. Okay, Florent?
Yes, thank you. Thank you for this presentation. Maybe I have a question a bit more related to, I mean, more for Antoine. Since you optimized a lot, I mean, you optimized the testing in with one of the goal at least to minimize the use of material. Could you also maybe go to another direction, which would be using another geometry of sample that could maybe save some material? Because in all the presentation, we were always using dent, but technically, I guess you could use any geometry, not any, but different geometries. And do you think that it would be possible or not really?
It's a good question, but thinking about it now, I don't have in mind a geometry that would be a lot more efficient than the dent one. Because you also have the fact that the dent specimen has some intrinsic advantages just as a ease of use. Because it's symmetric, and then there's also some nice things to use with this.
Yeah.
So I don't know. Maybe I could do some research to see some other geometries, but I haven't thought about it. So it's quite nice. Thank you.
One of the advantage also of the geometry is the easiness of machining. You have a simple rectangle, and with the tool that David showed in the beginning, it could be quite easy to pre-crack, and we have also something which is symmetrical. So we have to also take this into account.
Mm-hmm. Maybe I have another question for, I don't know who exactly, but could we think of any use of this somehow similar approach in fatigue testing, in fatigue crack propagation, and would there be any interesting output of this?
Can you mute again this guy, Pierre?
I mute myself.
I don't know what to say, but usually this kind of question, they are very good because that forces to think. But the problem I would see immediately with fatigue is that we will not have any geometric dimensional. So this homothetic behavior we have with the plastic zone, which justifies the capacity to separate plasticity from the work in the fracture process zone, we will lose that in fatigue, Florent. That would be the main difficulty. So everything works because there is extensive plasticity, and you can then start separating terms. So with fatigue, everything will be isolated, and we will be in small scale yielding. And I don't see how we can go beyond that aspect. That would be my first answer, a more negative answer, but perhaps it's because I'm thinking too narrow. I have to think about it.
From my point of view, I think statistics used in a lot of way we do experiments to improve many things, which would be either the error we make on the extracted parameters, or the number of samples we need to use. I think maybe we need to do more collaboration with people that do more just focus on statistics, and have a bit of an exchange with people that do statistics with the guy that does material science.
Okay. One final question. No? Well, if not, yeah?
Pascal, I will just add that the recording of the webinar and the slide will be on the website. So if you want to access it or share it for people that cannot attend, please feel free.
Once again, I go and see this toughsteel.eu website. Okay, so let's thank once again our speakers of this morning, and well, Well, thank you for your attention and attendance to this webinar, and well, have a good day, and already have a good weekend. See you and bye bye.
Thank you.